Okay, Argand diagrams. Sorry, it's Argand because it's a French mathematician, Argand, but we call them Argand diagrams. Sorry. Anyway, what's an Argand diagram? Okay, it's a pictorial way of representing a complex number. So I mentioned earlier that 3 plus 4 is a nice one to choose. Okay, an Argand diagram is essentially like a Cartesian set of axes. Okay. So Descartes and Argand, they're French mathematicians around at the time, so they've had a lot of input into this sort of work. Okay? But rather than label that the x-axis and y-axis, we label that the real axis and the imaginary axis, like that. Okay? So any real number gets plotted on this axis, any imaginary number on that axis. So for the complex number 3 plus 4, so you could plot that as 3 on the real axis, and then 4 on the imaginary axis, like that. Okay, and you can write it as a coordinate point. So there you go, quick and easy. Argand diagrams is just a bit like coordinates with the XY plane and Cartesian coordinate system. Okay, so that means any complex number could be put anywhere in this quadrant. So if I have 3 minus 4, its conjugate goes down there. If I have negative 3 plus 4, it goes up there. If I have negative 3 subtract 4, it goes down there. So anywhere in this, we call it complex plane, you can actually put one of these complex numbers, z. What we're often interested in what is the modulus and argument. Okay. Now if we draw as a vector this line segment, draw it as a vector from here to here, we're interested in what the modulus of that is, okay, often called r, and what the argument of that is. When we say argument, we mean what is the angle between the positive real axis and the vector we've drawn there, okay, r and theta. To do that, it's very, very simple, okay. Just consider this as a right angle triangle, okay, and this bit here, you can see, is just going to be r cos theta, and this bit here is going to be r sine theta. So what that means is, if you know what r and theta are already, you can convert them into xy coordinates. But if you know the xy coordinates and you want to get the modulus and argument, that's quite simple as well, okay? Because this here, this distance is going to be 3, this distance here is going to be 4, and this is Pythagoras' theorem to work out the value bar. So r squared will be 3 squared plus 4 squared. And in general, you could say r squared equals x squared plus y squared, okay? And then r is equal to 5, which is why 3, 4 is a nice number to choose, because it's a Pythagorean triple, okay? And if you want to work out the argument of that, of course, it's quite simple. You just do the inverse tan, say arctan if you want, of 4 over 3. Okay, inverse tan of 4 over 3. I don't have my calculator with me, but I know that's 53.1 degrees. Okay? So I'll use degrees for the moment. Okay. Later on, I'll get my calculator, because we can write that in radians as well. Okay, but I'm going to do it in degrees just for the time being. Okay, and in general, then, when it's in the top right quadrant, okay, the inverse tan of y over x is going to give us what the argument is. Okay, happy with that? Good. I'm so glad you said yes. Okay, so that's Argand diagrams. Okay, but what we're doing is we're finding the modulus and argument of complex numbers now. As I said, the modulus, which we often use in vectors, okay, is the length between the origin and the complex number. It's the closest possible distance between the complex number and the origin, and the argument is the angle. Okay. But what I'm going to do is I'm just going to put another example up on the board for you. I'm going to wall this off. I'm just going to change it slightly. Okay, I'm going to put down the complex number. Let's choose something a bit different. Okay, -2 plus 4i. Okay, I'd like to find the modulus and argument of that. Pause the video maybe. Done it? Good. I always recommend drawing an Argand diagram so you can see where it is. -2 plus 4i. It's there, isn't it? Okay, so the argument you need is that. That's the angle. Okay, that you need between the positive real axis and the imaginary axis. Okay, how are you going to work that out? I recommend you work out that angle there first. Okay, so if that is -2, 4 as a coordinate point there, then this length here is going to be 2, that length there is going to be 4, isn't it? Don't have to worry about putting negatives in when you're doing this. I never do. Okay, and let's just work at that angle. I'm going to call it alpha. Okay, Greek letters always for angles. Let's work about that. I don't need that. Okay, so what I'm going to do to work out what alpha is, I'm going to do alpha is equal to the inverse tan of 2 over 4, which is a half. I'm going to put 2 over 4 to make it obvious, and then we write down what the answer is. Okay, don't have a calculator with me. You can work that out and put it in. Okay, degrees for the moment, but in my next video we're going to go on to radians. Okay, there, so that's that. Okay, then of course to work out what the argument is. Now we often use argz as shorthand for the argument of z. Okay, the argument would be this angle. So 90 degrees plus alpha, wouldn't it? Okay, or pi over 2 plus alpha if you're doing it with radians. Okay, because I'm not doing anything, I was about to say complicated or complex. Because I'm not doing anything more advanced than this, we don't need to use radians. Okay, radians only come in when you start having calculus involved. Okay, so we can get away with degrees for the moment. Okay, so you can work out what that actually is. In terms of what r is, that's always going to be easy. So r is going to be the square root of 16 plus 4, so root 20. And you can always simplify that, can't you? That's 2 root 5. Okay. Now I'm just going to introduce to you one more thing, something called the principal argument. Okay. Yeah, I'm not going to put it on the board, the spelling of it. I'm sure you can work out how to spell principal. The principal argument is when you take an angle between 0 and pi, or 0 and 90 degrees, and negative pi and 0, negative 180 degrees and 0. I'm going to say it one more time because I think I missaid it. Between 0 and 180 degrees, 0 and pi, and negative pi, negative 180 and 0. Okay, that's called the principal argument. Okay, so you can either give an answer somewhere between 0 and 360 degrees, 2 pi, or between 0 and pi, negative pi and 0. Okay, that's what we call the principal argument. Okay, but anyway, I'm not going to go over any more examples. You can look those up. Okay, if you do have a complex number that's somewhere in that quadrant there, just draw out the diagram. Okay, and then just work out what, because you need to know whether the angle is going to be negative or positive, isn't it? Okay. Having said that, yeah, I will treat you just one more example. Let's just put it in. Okay, so they're very easy to make up. Okay, try to use one that I know the answer to. Okay, because I haven't got my calculator with me. Yeah, and there comes a point where you do need calculators, don't there? So I'm going to do 3 minus 4. That's the conjugate of one I chose before, because I know what the inverse tan of that's going to be. So, just because I've done it so many times before, that's why. 3 minus 4 is there. Okay, see? Just label those axes up. So that's the point, the coordinates 3, negative 4. Okay, so the argument we're looking for this time is either all of that, but can you see it's just easier to work out that, isn't it? That's where the principal argument comes in. Okay, so to work out that angle, we're going to first of all work out what this angle there is. Okay, I'm going to mark that as alpha. So that's 3, that's 4. Okay, so alpha is going to be the inverse tan of 3 over 4, and that's 39.1, 36.9. Yeah, sorry, 36.9 degrees. So that means that angle there. Argument of z is going to be equal to, and it's negative 53.1 degrees. Okay, because it's below the x-axis, below the real axis. Okay, so when the argument is below the horizontal axis, negative. Okay, and the modulus is just going to be 5, isn't it? Okay.